have got, oh, somebody just turned up to distract me. Here we go. We've got this section. I want to get through it. So I've actually gone through each of the questions and I've put them into various categories. And that's kind of going to be how today's going to work. The first bunch are all these questions where you're basically being asked from a given function, the intervals where it's increasing, it's decreasing, the local max and the local min, right? And we've covered that. So let's just practice at different kinds of functions. And then much fewer questions where you're only asked about concave up and concave down. And when we answer these questions, 12 to 14, won't it just be the second derivative that we'll use? Second derivative tells you about concave up and down. There's then 3 questions where they ask you everything. So what does everything mean? It means ask you these 4 things and these 3 things, right? Ask you everything. And so there are 3 questions towards the end that do that. And then the last bunch of questions are all to do with graphs. So they give you a graph and they say, look at this graph and tell me when is it increasing, when is it decreasing, whatever it might be. And those ones I'm not even going to do because we've pretty much covered graphs. So let's jump right in. I've got that one there as an example. I believe that's question 6. So I'm going to do an example where you're asked these 4 questions. And the first one I'm going to do is a polynomial. And since I'm only interested in increasing and decreasing local mins and max, right, then I'm not really going to do anything except the first derivative, right? I'm not going to worry about the second because they don't want to know about it either. Well, as far as derivatives go, would you agree this is one of the bread and butter questions? It's just power rule, nothing special. Multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. And you get that. Now we know that we've got to find the critical numbers. We've got to find, in this case, when the derivative is 0. So we are trying to solve a quadratic. And I'm a great believer in making life easy. So do not try and factor that guy because you'll be there all day. Tell me, well, that's a bad word, don't factor it. Don't factor it as a quadratic right away. Isn't there a common factor I can pull out first? So if you can see a common factor, pull the damn thing out. Because what that tends to mean is that the question becomes much easier to factor, doesn't it? Okay, factoring quadratics is not a skill that's going to disappear in calc. You're going to do it forever. So factor that guy for me.
5 and -2.
Which means we now have 2 solutions. This factor equals 0 when x is -5, and this factor, right?
Isn't it 3? Because 6, oh no, there's no variable in front. That's right.
Okay, we're good. Yeah, but it's worth checking because I do make mistakes. Now, once you've got this guy, what I then do is I create that number line. For me, this is the way that works best. Now, if you want to go online and look at other techniques, there's a table of value techniques that some people prefer. I'm not saying don't use that. It works well. You just pick what works for you. 4, 3, 2, 1, 0. These arrows mean that the function continues forever. All I'm going to do now is put in that the derivative is 0 there, and that the derivative is 0 there. And then imagine little walls. And there's my number line. And my number line is going to tell me all about the derivative. And then I do test points. And for this particular question, I'll need 3. Right, I'll need 1 for here. I guess I'll call that region A, region B, all the way from here to here, and region C. Right. Now, once I found whether the derivative is positive or negative in each of these three regions, I'm pretty much ready to answer the questions. So would you agree that x equals -6 would be a good test point for region A? Okay. You shouldn't need to guess who I'm going to pick for B. What x coordinate do you think I'm going to choose for B?
Zero.
You don't, yeah, God, I was going to say, you don't know me by now. I mean, 0, come on. What's the easiest, well, for me, what do you think's the easiest number to deal with? 0, right? Probably one of the simplest ones. I don't think I have really much room for the other ones, so I'm going to pick 3. And for each one of these test points, we find what its derivative is equal to. And I'm just going to do my shortcut way. That's positive, that's negative, that's negative. That makes everybody positive. When you plug in 0, that's positive, that's negative. That makes us negative. When you plug in 3, 6 is positive. 3 plus 5 is positive. 3 take away 2 is positive. Everybody's positive, so it's positive. And I have now got lots of pluses, lots of negatives, and lots of pluses. And now I can basically finish the question. Intervals where it's increasing, intervals where it's decreasing, local minimum values, local maximum values. So let's move this over here and see what we've got. Right, isn't it increasing when the derivative is positive? So it's these two outside regions. And I've been told, at least by 2 people now, that you can use the union symbol. So just go looking for it when you do WebAssign, and you can do that. Now, if I want to find out when is this function decreasing, it's from -5 to 2. You see little curly brackets? Now, I need to find, what else do I need to find? Local min and local max. Okay, I'll focus on this one at -5. Can you see it x equals -5? On the left, the derivative is positive. Then it's 0, and then on the right, it's negative. Can you see that? If I draw this little picture, can you see that's a local max? So I know that there's a local maximum at x equals -5. Let me check something here, because I've got the answer somewhere. But they don't want the local max, they want the local maximum value, which essentially means they want to know what the y coordinate is. So I will need to find f of -5, and the answer to f of -5 is eventually -68. So that's the number they're looking for, the y coordinate of the local max. And then they want the local minimum value. I'm assuming that there is one. -0, positive. Yep, that's at x equals 2. And its value is f of 2. And the minimum value. Oh, sorry, I got these mixed up. I was looking at the answer. The minimum value is that number, and the maximum value, which is this one, is 275. And that's really just start with this function, plug in -5 and cube it, plug in -5 and square it, plug in -5 and you get 278. And then if you do 2, 2 and 2, you get that number. So that's the number in front of me. So I'm assuming that WebAssign can count, even if I can't. From start to finish, that to me, that question has a nice flow to it, isn't it? You kind of do this first, this second, this third, finish, right? It's got a nice flow to it. Now that's what polynomials look like when you do those questions. So let's skip by the polynomial ones and do a rational function version. And the guy that looks like that is 8. So this one is going to represent any fractional power. So this could have been square root of x times x minus 8, right? Something like that. Anything that looks like that. The process is not going to change. The algebra might a little bit because solving equations change when functions are different. Would we agree, I hope, that this is a product rule? So it's going to be f dash j plus f of g dashed. If you differentiate this fella, you multiply by the power and you reduce it by 1. You leave the second guy alone. You leave the first guy alone and you differentiate by the second guy. And now we do style points. And style points is really indispensable. You can't really do this question unless you make this thing look pretty. And making it look pretty is making it is factor the heck out of it, essentially. Now you might look at that and say, what factor have I got? I don't see any. Well, there is factors. Do you see how that's x to the negative 1/3 and this term is x to 2/3? That means that x to the power of something is a common factor. Now we're going to do a common factor that's not typical. Normally you have an x cubed and an x squared and you bring out an x squared, right? I have an x to the 3rd and I have a 2/3. Which one of those two, because it has to be one or the other, is going to be my common factor?
The negative 1/3.
Yeah. Pick the smaller of the two. Now, if you do that, you're left with 2/3 x minus 8 here, and then something really weird. 2/3, right? X to the 2/3, take away this guy. So 2/3 power, subtract negative 1/3 power. What does that get you? 2/3 subtract negative 1/3. What power of x do you get out of that?
1/3.
1.
2/3 take away negative 1/3.
X to the 1.
You get x to the 1. Now all I'm going to do is distribute this. Bring this guy downstairs. Combine those guys. And there is the ugly derivative that we've got. 5/3 x take away 16/3. Now it might help, I don't know if it does. There's a slightly different version of the same answer. And here is a third different version of the same answer. Out of those 3 guys, I don't see any real, they're all correct. I don't think there's a problem. Out of those 3 guys, which one of those 3 do you like the looks of? Because that's the one I'm going to use from this point onwards once you pick. Do you like the top one, the middle one, or the bottom one? Which one do you like the look of?
I just have a question before I answer that one. But so
Go
far,
for
the
it.
second one looks the best to me.
You
But,
like that one? Right, that's what we'll do. What's your question now, Izzy?
After you distributed the 2/3, or
Right.
where did that x in the parentheses go?
Oh, where did it go? 1x
No, the
plus
line above,
2,
yeah, that one right there.
Right.
Where did that go?
1x plus 2/3 x becomes 5/3 x. Right.
Track it now, thank you.
So we have got this ugly guy, but they're all ugly, so it doesn't matter. And I'm going to use him now to find our critical numbers. So I'll just rewrite this guy down. Right, critical numbers. When is the derivative 0? which means we are trying to solve when is this 0? Fractions are 0 when the top, the numerator, is 0. Fractions don't care what the bottom is. The bottom doesn't make things 0, only the top does. And in this case, there is one of our critical numbers. But don't critical numbers also happen when the derivative is undefined? Is there a value of x that makes this derivative impossible to calculate?
0.
So we now have 2 critical numbers, not 1. So when I build my number line, they're going to be a 0. That's about 3 1/5. So 1, 2, 3, 4. So about there is where 16/5 lives. And about here is where the other guy lives. Now the derivative is 0 here, and I put un for undefined here. And then I'll do my little derivative guy. Right. Of course, function goes on forever. All right, I need to know some test points now. So imagine a little wall. Okay, give me a test point for region, I'll call me B and C again. Give me a test point for region A.
-1.
Can't use 0. Okay, I like 0, so I'll pick 1 and 4. Now, they seem reasonable, reasonable x's to pick, right? Now, I don't care what the number is, right? I do not care what the number is, whether it's, you know, the derivative -1. I don't care if it's 42 or 4.2. I just care it's positive or it's negative, right? So you're just going to trust me that if you evaluate this function at -1, you get a positive answer. If you evaluate it at 1, you get a negative answer. And if you evaluate it at 4, you get a positive, right? So this guy is positive. This guy is negative. And this guy is positive. And you're just going to say, okay, I trust you, but you can check it. And once I've got the number line, I can now do increasing, decreasing, local max value, and local min value. This function is going to be increasing when the derivative is positive. So that's going to be -infinity up to x is 0, and from 16/5 to forever. It's going to be decreasing in the middle. So that's from 0 to 16/5. If I look at this guy, it goes positive, undefined, negative. And the reason it does that is because there's a cusp there. So that's a local max at this point. So there's a local max at x equals 0, and its value is 0. So that's the number they want. They want the value of the function at 0. And this one here, negative derivative, 0 derivative, positive, that's the local min. The local minimum happens at 16/15. And I'm just taking their answer. According to them, the value of the function is about -10.42. So it's some ridiculous ugly number. Okay, so increasing, decreasing, local max, local min. The bottleneck, I think, my guesstimate is that the bottleneck is going to happen when you were differentiating the thing. And you had to factor it. If you just took, I don't know, if you took this guy as your answer, right? If you said, okay, that's my derivative, right? Can you see that there's no way on earth you're going to be able to find the critical numbers easily, if at all? Right? If I said, okay, that's it, tell me the critical numbers. You might get 0. I think 0 is doable. Do you think you'd get the other one? The 16, 15, the 16 fifths? No. You see why you need still points? You can't really do this question without being able to factor the heck out of the derivative, right? If you can't factor things, you're just going to go there and go, yeah, that's it. That's as far as I can move. So hopefully you'll get lots of practice at getting good at it, if you aren't already. Now, there are lots more situations, but we have a time limit. So I'm only going to do the next question, which is an example of a ratio. And I'm only going to do it as far as the critical numbers this time. So this is question 9. And we're looking at this guy. And if you do its derivative, I hope you all recognize that as a pretty standard quotient rule. Because f dash g, take away f of g dashed over g squared. Differentiate the top, you get 2x, leave the bottom alone. Take away, leave the top alone, and differentiate with g. And the whole thing is squared. Distribute 2x squared, take away 10x. Take away that times 1, that times 1, so what's that? Take away an x squared, take away is add. Combine like terms. That's a pretty nice looking derivative. But it's not finished. Can we do better? Remember, factor the heck out of it. X squared minus 10x plus 16. Come on, let's factor the heck out of that. What'd you get?
X minus 8 times x minus 2.
Would you agree now that that function is at his ultimate style point? Right, that's as pretty as that guy's going to get. But isn't that guy also very easy to find critical numbers with? How many critical numbers does this function have? Exactly. 3. Right, is it? 3. And can I just write them down as x equals 8, x equals 2, and x equals 5? Aren't 2 of them because the derivative is 0, and the bottom one is derivative is undefined. Now, at this point, if we had time, wouldn't I do another big number line? Wouldn't I break it up into bits? Wouldn't I be doing test points and saying this bit's plus, this bit's minus, this bit's plus, this bit's minus, and then we could go and answer all the questions. Right? There is one hiccup on this one. Hasn't happened yet. At x equals 5, isn't there a vertical asymptote? You can tell that from 141. Isn't that x equal 5 going to be a vertical asymptote? So when you are looking for local min and local max, don't go looking there. Right? That is not going to be a local min or a local max, right? Only go looking at these two places. So just in case you end up thinking that you found another one, and if you tried to do it, do you know the answer would be infinity? you know, the y coordinate would be infinite. That'd probably be a sign that maybe you shouldn't have chosen it. So that was a quicker version of that one. And the next one is also going to be a quick version. I'm only going to take this two derivatives.
I have a quick question.
Sure.
So I just finished my test.
Oh,
And for one of the questions, I did like some of my work just to find the derivative of the equation on like one of my notes. Do you want me to submit that as well to you?
I need to see every piece of working you could possibly give me. So yes.
Okay, thank you.
So we are going to look at a trig question. And how do you do all the things I just talked about? Right now, in this trig question, they've restricted your window from 0 to 2 pi. So you only need to do numbers from 0 to 2 pi. Right? Why did they do that? Why didn't they just say pick any x you like? There's a kind of practical reason for why they restricted it.
Because if you went higher, it's just the same circle over and over again. It's
Yeah.
the same thing. So they
So
kept
you'd end up
small.
having to write an infinite number of intervals, wouldn't you, amongst other things? So that's what that is. Now, the derivative of this guy is 7 cosine x's, take away 7 sine x's. And so where are the critical numbers? Well, we're now going to have to deal with solving a trig equation. So 142. How do you make or solve a trig equation? Well, it depends on what the trig equation looks like. Tell me what to do. I'd rather you told me before I just said, look, do this. I want to solve this. Tell me what I could do to get there.
Add 7 sine of x to both sides.
That's a good start. Yeah, that'll work. Then what?
Divide
Divide by 7.
Say it again.
x. Divide by 7 cosine x.
And if you divide by 7 cosine x, this guy becomes 1. And doesn't this guy become tan x? And now you are looking for places where the tangent function is positive 1. And there are 2 of those. In the first quadrant, at pi over 4, the tangent is 1. And there's another one in the third quadrant. Where else is the tangent function equal to 1?
5 pi over 4.
Yep. I get to see my little spiel again. Nothing you ever do from Math 99 onwards has gone forever. Isn't this solving equations strategy that you did in 142? Isn't it also unit circle, right? When is a tangent 1? When is a sine pi upon 3? You know, things like that are going to happen. So those little skill sets and little bits of rustiness, because you haven't used them a lot, are going to come up and bite your bum sometimes. And number line, and off you go. Let's do another one where we have a function that's got cell log in it. I want to do its derivative. Chain rule? Agreed? Chain rule? Okay. So log of something is 1 over something times the derivative of something. Let's find critical numbers then. What makes this derivative 0? X equals 0. Does this function have any undefined values? can the bottom be 0? No. So this guy is going to be one of the simplest looking intervals in the world. And why am I only starting at 0? Why am I not, sorry, I'll take that back. There we are. In this question here, aren't we going to have two distinct regions, a left side and a right side? So I'm going to do a test point in -1 and a test point in 1. I was about to say, why am I starting at 0? And then I talked myself out of it because I don't need to start at 0. I can have negative values because won't 1 squared or -1 squared still be positive? If that had said x plus 6, wouldn't I have to stop at the point where logs are negative? So that never happened, so I guess it doesn't matter.
Where do I submit my test?
You
Because
send it to me to my email, Cynthia. So drobertson@olympic.edu and just put it as a PDF attachment.
I did.
And you are done. You're just part of the class again.
Okay, thank you.
Yeah, you went and missed some really good jokes. Is that not right, Ethan? Cynthia missed some really good jokes. Let's move on to question, lost my pen. Did you lose a pen? Where you do concave up, concave down stuff. Try to find one. What is it? 12. I want to find 12. Or 13, or one of them anyway. Where are you? Okay. Oh, this one looks weird enough. I'll do that one. So we are being asked in this question, and they're doing that 0 to 2 pi because of the sine thing. We're being asked to find intervals where it's concave up and intervals where it's concave down and the points of inflection. So this is second derivative stuff. So to get the first derivative, I'm going to look at this as a chain rule. So it's 1 over 2 plus sine x times the derivative of 2 plus sine x, which is cosine x. So this is cosine x on the top and a 2 plus sine x on the bottom. And now I will find the second derivative. Would you agree that to do the second derivative, it's not a chain rule, it's not a quotient rule? Right, fraction. And it's f dash g, take away f of g dashed, all over g squared. So it's negative sine x times this guy. Take away, leave this guy alone, and differentiate that guy. And it's all over 2 plus sine x squared. I multiply through by negative sine x. Okay, we're on the hunt for style points. Okay, is there anything you can do to the terms on the top that simplify it so it looks a little bit nicer? Because there is. Can you see it?
Take out a -1.
So those two guys become -1. Is that what you're saying?
Yeah, you could just take out the -1, which in turn gives you the sine squared x plus cosine x, which is which is a trig identity.
Yes. So there's our trig identity. Sine squared plus cos squared is 1, but isn't negative sine squared, negative cos squared, then negative 1? If you pull out a negative 1, you can see it. Which means that we have made it look pretty. So I now need to find the critical numbers for this guy. Right, let's find out when the second derivative is 0. So I'm trying to solve when this guy is 0. Right, he's a fraction. If you're going to be a 0 and you're a fraction, isn't it the top has to be 0? Don't care what the bottom is, doesn't matter. So I am trying to solve that one. Okay, help me out here. Where do we go next? This is Calc 2 again. Not Calc 2, Trig, I should say. P-Calc 2.
At pi.
Oh, you're trying to decide what the answer is just by looking. That's probably a little bit too much in one go. Let's
Plus 1
try and
divided by -2.
okay. Yeah, let's go there, right? Can I check that? 2 plus sine x. Looks good. Looks good. Looks good. Okay. So which quadrant is a sine going to be? I'm puzzled a little bit, but my brain will get there in a minute. Okay. Which quadrant is a sine function negative? Which quadrants?
3 and 4.
Okay. When is a sine a half? In the third quadrant, negative half, I should say, and in the other quadrant.
7
That's
pi
good.
over 6.
Yep, and in the fourth quadrant,
11 pi over 6.
right? Have you got a nice unit circle? Because you should have one, guys. Because if you don't, well, I guess you could have a great memory. That's the other way of doing it. But have a unit circle handy if you don't. Okay, that is going to represent the only two critical numbers. But you say, wait a minute, the bottom could be 0, right? The second derivative could be undefined. Let's find out why it's not a problem. Isn't 2 plus sine x never going to be 0? 2 plus sine x will never be 0 because 2 is much bigger than 1 and sine x can only get to 1 and minus 1, right? So it will never kill it. So we are going to have a number line starting at 0, finishing at 2 pi, and go 1, 2, 3. So I know that's not really 2,6 pi, but if I call it 2,6 pi, you know. I just did my little increments in 1/6. So we have a region here, call it A. We have a little region in the middle, call it B, and a tiny little region at the end, call it C. And we are going to find out by doing test points in each of the three regions whether the second derivative is positive or negative. So I'm going to do some test points. Right, I want somebody in this region here. And it doesn't matter who I pick. I'm going to pick a half pi because I like it. And then I've got somebody from here to here, and I'm going to pick this guy, which is 3 upon 2 pi. And I'm going to have to pick somebody here, and I'm going to pick 2 pi. Have you any idea why I chose versions of half pies? I could have chosen, 4, 6 or something, right? But I chose those guys. Any ideas why?
Because they're all like perpendicular things where
Yeah, they're all
it's
nice numbers, right? They're all nice numbers, right? Zeros and ones typically. So I can put those in and come up with my answer. So this fella here, you trust me, ends up being positive. So that's this one. And these two end up being negative. So this test point gives me a negative second derivative. This test point gives me a positive second derivative. The last one gave me a negative. I can now do concave up. Concave up is when it is positive. So that's going to be from 7/6 pi to 11/6 pi. Concave down is going to be when it is negative, and that's from 0 to 7/6 pi, and then from 7/6 pi to the end, which is just 2 pi. And it has 2 points of inflection. One of them is at 7/6, and the other one is at 11/6. And those guys have coordinates. And I'm just writing their answer down, you can check it. When you plug 7/6 into the original function, what the heck is the original function? That guy, you get this. And you plug in 11/6 into the original function, this guy, you get evidently that guy. And that is an example of concave up and concave down. These are not short questions, right? There's a lot of stuff that needs to get done just to answer when is it concave up and when is it concave down. So for my last question, I'm going to do one of the do everything guys. So let's find a do everything guy. Question 15. Okay, you're going to have to get an abbreviated version of this fella. Got 4 minutes. This fella, this fella. That's the first derivative. If I take out 4x as a common factor, if I then factor it a little bit more, I get that guy. You comfortable about so far so good? Now, in this case, there are 3 critical numbers, 0, -2, and +2. That's going to give me a number line that looks something like this. And x equals 0, the derivative is 0. At -2, the derivative is 0. And at +2, the derivative is 0. And if I use my test points, it's positive here, it's positive here, it's negative here, and it's negative here. Can you just trust me that's what you get? Now, from this number line, if we had time, couldn't you tell me the intervals of increasing and decreasing? And couldn't you also tell me where all the local max and mins are? Would you agree we could do that? If we had time, we would. But what I'm going to do instead is I'm going to return to this guy. And now we're going to continue onwards and do the concave up and concave down stuff. Why did I write my first derivative in this version and not in its style point version? There's a practical reason for why I wrote the derivative like this and not like that.
It's easier to differentiate.
Yeah.
Or
Just made my life easier. Great believer in being efficient. Another power roll. Okay, we're going to make it look as pretty as we can. I don't know how pretty this is going to be, but I'm going to try my best. Anything you can do here?
A lot of work.
Yeah, I don't think there's much benefit in pulling out a 4, but yeah, I could. Okay. Now, you could do that as a difference of 2 squares. To be honest, I don't think it's worth it. Because aren't we just interested in when is it 0? So it's going to be 0 when 3x squared minus 4 is 0. That's going to be when 3x squared is 4. And that's going to be when x squared is 4/3. Which means we are looking at plus or minus the square root of 4/3. Which means we are looking at plus or minus 2/√3. So I'm not sure what 2/√3 looks like as a value, so I'll tell you right now. 2 divided by the square root of 3 is about 1.1. Okay, so if I make this 1 and I make that 2, there is where 2/√3 lives. And if I make that 0, I'll make that -1 and -2. Then about here is where -2/√3 lives. And our second derivative then is 0 at these locations. I would then do a test point of -2, a test point of 0, and a test point of 2. And if I did that, I get positive in this region, negative in the middle, and positive on the end. And can you see concave up in this region and in this region, concave down between these two numbers? And wouldn't this be the x coordinate of a point of inflection? And wouldn't this be the y, the other one, the other x coordinate of a point of inflection? Okay, whew, that was tough, but we got there. Hopefully, I've given you enough, ideas to be able to complete those. I guess I'll find out when you do your homework. Hopefully, it works. Say hi and bye bye.